Hello and welcome to Pre-Calculus, Section 6.5, Applications of Log and Exponential Equations. So in this unit, we're going to talk about math modeling, and we're going to limit it to three types of scenarios. The first one being compound interest, the second, population, growth and decay, and also radioactive half-life. So briefly, what is meant by mathematical modeling is that mathematicians in various fields are attempting to determine an equation that they can use to make predictions into the future. So time would be your input, your x-axis, and the measurable output would be your y-axis, and these three phenomena that I mentioned all behave exponentially, meaning an exponential equation can be used to make predictions about the measurable outcome in the future. So you want to take notes on this page here because we're going to use formulas in this section. So the formula for interest compounded continuously is this one here. P of t is P0 times e raised to the r times t. So your inputs are your initial investment, P0, your interest rate, R, and t is your unit of time. All right, then this one says the formula for interest compounded n times per year is given by this formula here. So the variables are the same here for P0 and R and t, but you have this additional variable n, where n is a whole number. The whole number n is how many times per year that your interest is compounded. All right, and then here we're talking about population, growth, and decay. So your formula for exponential population growth is this one here, where P0 is your initial population, K is your growth rate, so that's a percentage of growth, and T is your unit of time. And then the formula for population decay is very similar, the only difference being the negative sign in your exponent here. And then radioactive half-life, the formula for radioactive decay is this one here, where A0 is the initial amount of material, usually given in a weight unit like grams or pounds, kilograms. And the A here, this one, is the amount of material left after T years, T given years, and K is your decay constant, which is a rate given as a percent. So let's look at these two graphs here. So when your exponential function starts out small and then rises very rapidly, this is exponential growth, and that happens when K, your rate, is greater than 0. Okay, so then here, if your exponential graph starts out large and decreases fairly rapidly and then levels out close to 0, like this graph here, then your K, your rate, is less than 0. It's negative. So this would be decay. You've got a negative in the exponent. This would be growth. You've got a positive in the exponent. Okay, so the first example says find the time it takes for $5,600 to double when invested at an annual interest rate of 6% compounded continuously. So I'm going to highlight the important information here. So we've got initial investment of $5,600. We want to find the amount of time it takes for it to double. We've got an interest rate of 6%, and we're told that it is compounded continuously. So we want to go back and find the formula that applies for compounding continuously. So I can see back here that the formula for interest compounded continuously is this one here. So I'm going to write this formula down. The next thing I'm going to do is identify which constants I'm given in my problem statement. So your initial investment is P0. In our problem, it's said that it's 5600. And then we're told to find out the time when it doubles. So what that's telling me is that if I double 5600, that would be 2 times 5600, which is 11200. That's going to be my P. All right, and I'm also told my rate. My rate is 6%, and we always want to write that as a decimal number, so that means I move my decimal point. So if you're given 6%, remember I would move my decimal point 1, 2 places to the left, and I would write it as 0.06. So now I want to go ahead and substitute those numbers into my equation. So I'm going to have 11200 is equal to 5600 times e raised to the 0.06 times time. All right, so you don't necessarily need those parentheses around time in there. All right, so now I want to solve for t. So the first thing I'm going to do is I'm going to divide by 5600. So I can cancel this out, and I already know this is going to be 2. So let me just stop right here a second and tell you that if you've got a double problem, you always know that you're going to have this 2 over here. So you can start out by just saying that 2 is equal to e to the point, whatever, 0.06 in this case, times t. All right, so the time to double is going to be constant for the problem at hand. All right, regardless of what your initial investment is. All right, so now I got to solve for t. So to undo an e and get to the t, I need to take the natural log of both sides. So I'm going to take the natural log of both sides. So that allows me to cancel out this. So I've got the natural log of 2 is equal to 0.06 times t. And then if I divide by 0.06, I'll say that t is equal to the natural log of 2 divided by 0.06. Now this is one of those times when we really want to see what the magnitude of that number is, so we want to punch that into the calculator and figure out what we're talking about in terms of years, so it's not exactly clear what the ln of 2 divided by 0.06 is unless we punch it into the calculator. So here's Desmos Scientific, so I'm punching in, let me just blow it up a little here, ln of 2 divided by 0.06, and I'm getting 11.5524. So you want to keep, for our homework reader, 4 digits to the right of the decimal point unless told otherwise. So this is our answer. 11.5525 years is how long it takes for our initial investment to double. Our next example says the population of the world in 1985 was 4.8 billion. The growth rate of the population was 1.5% annually. Predict the world population in the year 2005, assuming exponential growth. So we're modeling exponential growth of a population. So let's go back and look at our formulas. So I can see that population growth and decay, this one would be growth because it has the positive k. This one would be decay because it has the negative k. So this is the equation we're going to use. So sometimes you'll see the rate written as a K, sometimes as an R. It doesn't really matter what letter you use. This is your rate right here. All right, so let's highlight the important information that we're given. So the population of the world in 1985, so this is your initial year, was 4.8 billion. The growth rate of the population was 1.5% annually. And it says predict the world population in the year 2005. So that's your end year. All right, so let's see what we can get out of this. So your initial population at your beginning time of the interval you're talking about is said to be 4.8 billion. All right, so your initial time, let me just call that T0. So this is P0. Your initial time, T0, is 1985. All right? And then we're going to a time T of 2005. So we're interested in how many years have elapsed. And that is the amount of time that we want to input into the equation here. So if we subtract 2005 minus 1985, that's 20 years. So we're going to input T as 20 years. All right, and so that's T minus T0. That's 20. All right, so this is the number we want to put into our equation, the time that's elapsed. The next number we need is our growth rate. So we're told that it's 1.5%. So we're calling it K in this equation, 1.5. So remember, we want to move the decimal over 2 places, so we're going to enter it as 0.015. Okay, now we want to go ahead and put those numbers into our formula. So P is equal to 4.8 times e to the 0.015 times 20. So all of the values are known on the right-hand side, so we don't have to take the natural log. This one, you can just type that whole thing in there and get out a P. So I've gone ahead and typed it into Desmo Scientific, and this is how it would look if you typed it in. So if you've got 2 numbers in the exponent, you're going to have to put parentheses around them, and then you would multiply. This is a multiply in between here. All right, and then you're going to get out, go over here, a value of 6.4793. So this mathematical model predicts that the population of the world in 2005 would be 6.4793 billion people. All right, so let's look at example 3 and determine which governing equation we need. So it says in the lab, a bacteria culture has an initial count of 255 bacteria, and the population grows at an exponential rate. After 12 hours, there will be 1,000 bacteria. Predict the population of bacteria after 24 hours. How many hours should it take for the population to reach 1 million? So it looks like we're talking about population growth, exponential rate. So we're talking about the same equation. Population growth with a positive K. So we want to go through and we want to find out what information has been given to us. So we have an initial count of 255 bacteria. It says after 12 hours there will be 1,000 bacteria. And then it says predict the population after 24 hours. And there's another question that says how many hours should it take for the population to reach 1 million? So we've got several questions we're being asked here. Let's start with the first one. So we're given a P0 here of 255 bacteria. So our initial population is 255 bacteria. All right. And then it says after 12 hours, so there's some elapsed time of 12 hours, there are going to be 1,000 bacteria. So I could say at some time t equals 12 hours, you've got 1,000 bacteria. All right, now let's break that down. Now we don't know what the rate is here, so K is unknown. Okay, but we do know time, and we do know P0, and we do know P. So let me just move this arrow over here. So this is P at time t is equal to 12. So we have enough information if we substitute that into the equation to back out what the rate must have been to allow that bacteria population to grow from 255 to 1,000 in 12 hours. So if I substitute P on the left, P0 on the right, we don't know what K is, but we do know that time was 12. Time is 12, unknown K. All right, so we're going to have to use natural logs to get that K out of that position there so we can find out what the rate was that caused this to happen. So let's divide by 255. All right, so I've got 100,255 e to the 12k. So we're going to take the natural log of both sides. We needed equals natural log of e to the 12k. All right, so that allows us to cross out this. So we have 12k is equal to the natural log of 1,000 over 255. So if I divide by 12, I'll have k is equal to that there. So instead of getting a decimal approximation in the numerator and then dividing it by 12, you can get a more accurate answer by putting this whole thing in at once. So then you don't have compounded rounding errors. So you would go ahead and type it in all at once like that in Desmos Scientific, and you get an answer of 0.11387. You want to keep a significant number of digits. You can lose accuracy very quickly if you round any closer than 4 digits on an exponential problem because they're very sensitive to the accuracy of the rate. So the rate is 0.11387. Okay, now let's go back to the question and see what we're being asked. All right, so the first thing it says is predict the population of bacteria after 24 hours. All right, so now we have the rate. Our time would be 24. Now let's see, what would be our population, our P0? So we're going to use the same P0 because we're making the assumption in these kinds of problems that the rate is the same at any of the times. So if our P0 is still 255, our elapsed time would be, in this case, for that question, 24 hours, and we have the rate. So the only thing missing then is your P. Okay, so I wrote all that information down. Now we're going to plug that into, this is P0. We're going to plug that into our equation here and get P is equal to 255 times e to the 0.11387 times 24. All right, so everything's on the right-hand side of the equals, so you can just type all that in there. You're going to have to be careful that you put the exponent in correctly. So let me write it like this. This exponent would all have to be inside parentheses in the Desmo Scientific or most calculators, so that it knows that both of these things up here are in the exponent. All right, and you can put a dot in between them. All right, so if you type that in, you should get it makes more sense to call it 3,921 bacteria, but I don't think our homework system will take it. The more decimal places you keep to the right, the better off you are with this homework system. Okay, the last question says, how many hours should it take for the population to reach 1 million? So we don't know what time is here. We're trying to figure that out. So time is going to be your missing variable. But we do know we want the population to reach 1 million. So that means for this question, P is 1 million. All right. So that means our rate hasn't changed and our P0 hasn't changed. But we're trying to figure out the time that it takes to reach 1 million. So that means 1 million is equal to 255 e to the 0.11387 t. All right. So t is in the exponent there, so we're going to have to use natural logs to get that t. So we're going to divide by 255 on both sides. All right, so we'll have 1 million divided by 255 is equal to e to the 0.11387 t. So I want to take the natural log of both sides. So I'm going to take the natural log of this. Both sides, and then I'm able to cancel out this here. So this is what I have now. Now I can just divide by 0.11387 on both sides, and I'll have t. Now I want to go ahead and put it in exactly like I have it written here so that I don't lose any accuracy by rounding this before I divide it by this. All right, so you can go ahead and type it in exactly like you see it, and you should end up with t is equal to 121.3 hours it takes to reach 1 million bacteria. So as far as, well, like I keep repeating, you know by now that the homework inputting system is fairly sensitive. So rounding to the tenths is usually not enough. So take it out a few more digits there. All right. All right, here's another example. It says a certain known radioactive substance decays by 35% over 500 years. Find the half-life of the material. How many years will it take for a sample of 500 milligrams to decay to 10 milligrams? Okay, so we're talking about radioactive half-life here. So let's go back and see what formula we need. So our formula is A of t is equal to A0 times e to the negative kt. So this is a decay, meaning your exponential graph is going to go down over time. So you're going to lose radioactive material over time as this material decays. So I've written down the formula. Now, it doesn't really matter that these are A's instead of P's. The formula is the same. So if you get a P in here and a P0 in here instead of an A, it's not going to affect your final result. All right, so let's go ahead and see what we have given to us. So I'm going to highlight the important information. So a certain known radioactive substance decays by 35% over 500 years. We're asked to find the half-life of the material, and we're also asked to find how many years it will take for 500 milligrams to decay to 10 milligrams. So we're asked several questions in this problem here. So we're told that it decays by 35% over 500 years. So we've got a span of time of 500 years that we know. So what this 35% decay is telling you that if you started out with an initial amount of P0, you've lost 35% of that P0 over 500 years. So think about it this way. You've lost 35% of that amount. So you're left with 65% of your initial amount. Let me just go ahead and make those A's. I've got two variables going on here. All right, so you can think about it this way. If I start out at A0, in 500 years, I get an A that's 65% of A0. All right, and we don't know the rate yet, but we can calculate it with this much information. So let's go ahead and put that into our equation over here. So this is your A. And then we know that T is 500 years. T is 500 years, so our K is missing, and we can calculate it. So we can find out what is the decay rate that causes you to lose 35% of your initial weight of the material over the span of 500 years. All right, so I'm going to cross out my A0 here. So I've got 0.65 is equal to e to the minus 500 times k. All right, I need that k, so I'm going to have to take the natural log of both sides. All right, so that's going to allow me to cross out this, and I'll have the natural log of 0.65 is equal to negative 500k. So I need to divide both sides by negative 500 to get k. So what I'm left with is k is equal to the natural log of 0.65 divided by negative 500. All right, so you're going to need to keep this negative in there for sure. If you make a mistake and put in a positive number, you're not going to get the correct result. All right, we want the rate to be positive, but the natural log of a fraction, this is basically a fraction, is a negative number. So that you'll end up with a negative over a negative, and that's why you're going to get a positive rate. All right, so make sure you got that negative in here. Now, looking at how it would look if you input it into Desmo Scientific. All right, so there's your negative in the bottom, and you end up with a rate that's given to you in scientific notation. All right, and what you want to do is you want to move your decimal place 4 places to the left. This is what scientific notation tells you to do with this times 10 to the minus 4. So I've got 1, 2, 3, 4. 1, 2, 3. So my k is equal to 0.0008615,658, and that's going to use, that's the k I'm going to use. All right, so I found out what my decay constant is here, my rate of decay, and I need that rate in order to find the half-life of the material. Okay, so when I'm finding the half-life of the material, I can think about what I did here. So this here, A is equal to 0.65 A0, tells you how long it took to end up with 0.65 of the material. But we want to know how long it takes to end up with 0.5 of the material. All right, so if you think about this is another way of looking at it. For the first part of our problem, A divided by A0 is 0.65. Okay, for half-life, A divided by A0 is always going to be 0.5. Okay, so we'll have a 0.5 on the left-hand side of our equation. So what I mean by that is if I divided both of these sides by A0 to put it in the necessary form, A over A0 here, we can say if we're trying to determine half-life is 0.5. So our equation is 0.5 is equal to e to the minus kt for half-life. And what the meaning of half-life is this is a time. What is the time it takes for your radioactive substance to decay to half of its weight? All right. So now we know K because we just figured it out. So I can put K in there. Then the only thing that I won't know is my time, and that's defined as your half-life if you've got a 0.5 over here. Okay, the time that it takes to decay to half of your original weight. All right, so there's my equation with my K substituted in. So I'm going to have to take the natural log of both sides, which will allow me to cross this out, which will give me this equation. And now I just want to divide by the rate, making sure I get that negative in there because this is a decay formula. Now I can type that into Desmos.com Scientific, and this tells me that it'll take approximately 804.52 years for this radioactive material to decay to half of its weight. So let me just remind you one more time that these are very sensitive to the rounding in the exponent. So do not truncate your rate, put it in with a significant number of digits like this here so that you get a pretty accurate answer. You can mess around if you want to on the calculator and see how much of an effect it would be if you put in like 0.0009 or something like that. So don't round your answers until the end of your problem. All right, and then you go ahead and can do some rounding, but be careful because it's very sensitive how it'll accept your homework problems, as we know. Let's do the last part of the question now. It says, how many years will it take for a sample of 500 milligrams to decay to 10 milligrams? Okay, we know our rate. All right, we don't know our time. That's what we're going to figure out. All right, so our initial amount of material is 500 milligrams. And it's decaying to an amount of 10 milligrams over time. And this is the same rate we calculated, which is characteristic of the material. So if I substitute all these numbers in here, let's do that. I should be able to take the natural log of both sides. So I want to divide both sides by 500. And I will get that. And then I want to go ahead and take the natural log of both sides to get the t. And I'll get that. And now I can cross off the natural log and the e. And my equation becomes this. Now I'm going to solve for t by dividing both sides by the rate. So I'll have eventually a positive number because the natural log of 1 over 50 is going to be negative. So I want to type that into the calculator like that without rounding until the end. And you're going to get t is equal to 4,540.6 years. So this is how long it takes for this substance to decay to half of its original weight. Okay, and that's the definition of half-life. So example 5 says, demand for a product follows the relationship D of P is equal to 1650 times 0.89 raised to the P power, where D of P is in thousands of units and P is in dollars. So we're asked, what is the demand when the price is $20 per unit? And the other question we're asked is, what must the price per unit be to achieve a demand of 1,500,000 units? So the first thing that's different about this scenario is that you're asked to follow this certain law here. So this is your mathematical model. So this is not a base E problem. This is a base 0.89. All right, so this is where your base is, 0.89. Okay, so your input is price and your output is demand. So this kind of a situation might be used in economics or finance, where you need a price-demand relationship so you know what the effect on the demand is for your product if you change your price either up or down. All right, so usually what happens is as the price increases, the demand decreases, and as the price decreases, the demand increases. So there's an inverse relationship. Okay, so let's answer the first question. What is demand when the price is $20 per unit? So that's my known quantity. My price is $20 per unit. So I can substitute 20 in for P. So I just put 20 in the exponent position. So now let's look at how you would input this into the calculator. So this is Desmos Scientific. So you would go ahead and use your A to the B button, this one here, so that you can put in your A, raise it to the B, and then you get 160 point, all those decimal places. So I get the demand is 160.429 units. But let's see, is this units or is there something else going on here? Thousands of units. So we have to make sure we understand how to deal with that. D of P is given in thousands of units. Okay, so and what that means is we have to move the decimal point 3 places to the right. All right, so D would equal to 16429 units. However, it's asked for in your homework problem, whether they want the thousands of units, for instance, or the number of units. You'd have to read carefully. All right, so this is an example of a problem where you're going to use the relationship that you're given in the problem statement. That is the law that governs the behavior in this example. All right, so we have one more example here. It says $50,000 is invested at an interest rate of 4.5% per year. Find the value of the investment after 10 years for the following compounding methods. So we're talking about compounding interest here. So let's go back and see what our governing formula is for that. All right, so compound interest, if we're compounded continuously, we've got this base E here function. All right, and if we're compounded n times per year, so not continuously, a certain number of discrete times per year, where n is the number of times per year, then you're governed by this formula here. Okay, so I'm looking through here and I'm asked for annually, semi-annually, monthly, daily, and continuously. So continuously is your base E formula, but annually means you're compounding 1 time per year. Semi-annually, what that means is that you're compounding twice per year, once every 6 months. Monthly means you're compounding every month, so that's 12 times per year. And daily means you're compounding every day, so that's 365 times per year. Continuously means you'd have the function p is equal to p0 e raised to the rt. All right, so for the other ones, you're governed by the function p is equal to p0 times 1 plus rate over the number of times raised to the number of times the number of years. All right, so this is our formula. All right, so we're asked to compare, so we want to find out basically what your n, what the effect is that your n has on your compounding. All right, so let me just scoot that up to the top so I can write it all out on this page. So I'm given some information here in the problem. So I'm given my initial investment. So that's your P0. P0 is $50,000. You're given your interest rate, and we want that in decimal form, so that would be 0.045. And then it says after 10 years, so that's T in years. T is 10, so we want to work in years for the following compounding methods. Okay, so now I'm going to take P0, R, and T, and N for A through D, and set up my equation. I'm going to write those down. So what I did, I went ahead and plugged in my N's into the formula for each of these cases. So your N goes in this position here. So for annually, my N is 1. So here and also here. So there's two N's, here and here. When N is 2, here and here. N is 12, here and here. N is 365, here and here. All right, so let me just show you how that would look in the calculator. All right, so you can input the equation like this, and then you can go ahead and just change your N's and run it through again for each of those 4 scenarios. All right, so over here you would be given your P. So we'll round to the cents, so this would be 77648.47 dollars and cents. Okay, so I wrote down what I got by typing in my equation, changing my N. So you can, if you look at the trend, you can see that as N increases, that's the number of times your interest is calculated and added on to your principal value. So as it increases, your savings account will go up faster. The more times it's compounded, the more money you're going to have in your account at the end of the year. All right, so now let's do the continuously compounded equation down here. So I'm substituting into this equation here, P0 e to the r times t, which is still 10, and I'm getting $78,415.61. So this is the most of all of the options here. So compounding continuously will increase your savings account fastest. So we can even make a conclusion if we wanted to here. We can say that the more times you compound in a year, the more interest you'll earn in a year. So this is an example of a type of a problem you would have to do in business calculus or business in a finance class or something if you were a business major. Okay, so that wraps up the examples I wanted to work with you. So I hope you took good notes. So give your homework problems a try and let me know if you run into any questions.